In this video, Lee's going to continue with the implementation of Well 512, focusing on the core functionality. Lee?
Right. This will give us what we need to actually generate our sequence of random numbers, at least if I code it right. So we'll find out. We're going to make a new public method. It's going to return a double. We're going to call it next. It's not going to take any values in it. And the whole purpose of this method is to do all of the bit shifting, all the number crunching to give us the next number in the sequence. And we're going to use this as the core of our random number generator, and in the next video we'll come back and we'll add the ability to get the next number but force that new random number to be within a range of numbers.
Gotcha.
So let's get the first part of it going first. We're going to need some variables to hold. I always do that. But we need some variables to hold the information as we're shifting it back and forth. So I'm going to make 4 variables, A, B, C, and D. I'm going to make these uints. So again, same reason, we're going to just keep everything 32-bit for this initial pass, and then we'll come back later and we'll change these to ulongs. So our first action is to get the value that is held at index. So if you remember from the last video, I said that when we go in here, we're going to initialize our array and we're going to set the index to 0. So the very first time through, we're going to be returning whatever's an element 0 of the state array, which should be our seed. And then we've populated all of the other elements of the state array with just a continuously incrementing count of seed multiplied by 47 each time through. So it's almost like seed multiplied by 47, then that our product multiplied by 47 again and again and again until that number just gets to the end. And if it overflows, it's no real big deal because we're just trying to put in essentially a random sequence of ones and zeros throughout the entire state array. You can kind of think of the state array as a register of 512 bits, and then we're just shifting back and forth between those bits in a very precise way. So the next operation that we're going to do is we're going to take our state, and the index that we're going to be pulling is going to be index plus 13, and then we're going to mask that with an AND with 15. So this will ensure that we don't go above all of our elements. It's almost like doing a modulus and making sure that we don't go greater than. Third operation is going to be setting A or B to be the result of A XORed with C, which is then XORed with A that has been shifted to the left by 16 bits. All of that will be XORed by C, which has been shifted to the left by 15 bits. Next operation is taking C, setting it to what is stored in state of, let's see, we need parentheses. So this will be index plus 9. Is it going to pop up? Nope. Okay. So, all right, so it's going to be index plus 9. Again, I'm going to mask it with 15 to make sure that I don't overflow the array. Semicolon. Then we're going to take C, we're going to XOR it with itself that has been shifted 11 bits to the right. take that and then set state dot index to be equal to B XORed with C. Then D equals A XORed with A shifted to the left by 5 bits. Then masked with 0x DA 44 2D20. Yes, it's a magic number. And where that's coming from is right here.
As a matter of fact, that's where all of the magic numbers are coming from, just to point
Yep.
out.
Yeah, this is, there's some mathematical theory behind this, but I'm not privy to what that is. So I haven't found any papers that explain step by step what each one of these are doing.
Or why they're doing that, I mean.
Or why they're doing
Yeah.
it. It gets, some of the theory that I've read gets really complicated. They start talking about doing second and third and fourth derivatives of stuff. And the process is a recursive one when you look at it, because we're shifting all the stuff around. We're resetting states and we're saving it. And then the next time we come around, our state or the state array is in a different state. We shift some stuff around again, and then we get a different output. So in a way, it's almost like magic. But people who have spent an awful lot of time in school and have like PhDs have figured this out. So I'm going to rely on their expertise on this one. So we're going to take index, and we're going to set it to be index plus 15. Also mask it again with 15 to make sure that we don't overflow it. So this is resetting index for our next value. And then we're going to say A equals state of index. And then take state dot index and set it to be A XORed with B, XORed with D, XORed with A shifted to the left by 2. Stick your left foot in, shake it all about. XORed with B, shifted to the left by 18. XORed by, C, shifted to the left by 28, and semicolon. All right, now once you've done all that, we can return our state index divided with cast to double int max value divided by 2.0. So what we're doing is we've done all of the magic bit shifting and manipulation. We've gotten that final value, which is saved at state index. We're going to divide it by the max integer value casted to a double divided by 2. This is going to basically massage the number so that the output that we get is going to be in a 0 to 1 range in a double. So we'll get more precision than if we were to cast it as a float. And then it also primes the entire state array for its next pass through. So like I was saying, all this number is in an iterative process. So every time you call next, you get the next number in the sequence. It does all these bit shifting, setting up the state for the very next time you call it. So the next time you call it, it goes through, runs it, and you get a new number. So every time you will get a new number out to 2 to the power of 512. Which is, once again, more particles than what are in the universe, allegedly. Because I haven't seen that paper with the report of the final count. So if I build that, that's successful. We can come back up here to main. Now, we'll comment out this one. And we need to start off a new var up here. And this will be, let's call this one myrand equals new myrandom. And I'm going to give it the same seed of 20.
Okay.
Now down here, I'll just type it. It's not that much. Var rand equals myrand dot next. So build, no errors. If everything works right, we should get some random numbers. Well, I hit F5. Did it run? Did it not?
See anything?
Huh. Okay, I'll do it that way then. All right, so 1 million operations took, less than a quarter of a second. Our distribution is really, really close. So at the most, we're at 100,318. On the low end, we're at 716. So right at about 600 between the highest and lowest. Average is just under 5, but fairly close, and 116 duplicates with 1 million operations.
Not bad.
Now, one of the things that I said I wanted to do, and this is what basically I found by mistake, and that was if I was copying code by or based off of the paper, which designated using unsigned longs. So I initially used ulongs in these values as opposed to using uints. So if I go in here and I change this up to ulong, I need to change this to ulong, and I need to add ul at the end of our magic hex number to make sure that everything works there. Build out. See if F5 will work again. Nope. So now, we're off. So I've only got the first half. So are duplicates, but what did I mess up? Oh, it's still, this one's still, yeah, it's, no, what did I miss? I missed somebody.
What about the seed that you take in?
No, that shouldn't matter.
Okay.
Because it's multiplying that number. Wonder if that's supposed to say uint. Nope, definitely not.
Thank heavens, because I was thinking that'd be very weird.
Yeah, so let me go through the code again. This is what happens when you take a day off.
Yeah, that's true. For those of you that don't know, we're just now picking back up the session with 1 day off for handling other emergencies. Lee, are you just randomly clicking stuff now?
No.
Oh, it worked.
No, I wasn't randomly clicking stuff. But now we've got 0 duplicates. We're closer to 0.5 than we were before. Speed is about the same. Distribution, what's my largest number? So 100,025. And lowest is 617. So we're still at about 600 difference. But we've got no duplicates now. So we get a little bit more precision out of it, a little bit higher quality numbers.
Yeah.
And we still got a really good distribution. Though technically, we can argue that this is no longer the well 512 because we are using U longs. So in effect, we've doubled the size of our state array because now this is 1024 bits and not 512.
Cool.
But, this is a game.
Zero duplicates. So, I mean, I think we're set.
Yeah, out of a million numbers. So, I mean, your computer is fast enough. We could literally just go up here and have some fun with it. And still not sure why F5 doesn't work for me anymore.
Yeah, it's weird.
But so we'll run it with what's this one going to be? 16 million, I think.
Yep.
Yeah. So 16 million iterations, less than 5 seconds. Good distributions, really, really close to 0.5, 0 duplicates.
Nice.
So I'd say that is highly accurate, especially if we compare that back with our first run. So if I run through that real quick, give it a sec. Oh, that's not going to run because I hit F5. F5's broken today. So this method is a little bit faster. We're at under 4 seconds. So this one's about half of a second faster.
Mm-hmm.
So good distribution. And a little bit closer to 0.5 than our method, but almost 60,000 duplicated numbers where we had none. So.
All right, very cool. Well, so does that pretty much wrap up everything you wanted to do for the core functionality?
Yep, for this one. So we've got our random numbers working. They're coming back in the range that we expect them to be, and everything seems to be working fine. So the last thing I'm going to do is take this number and drop it back down before I forget. So we only generate 1 million test numbers. So when we come back in the next video, we can modify our code so we can bring back different ranges of numbers other than 0 to 1 all the time and force our user to multiply to get a range. So we'll be able to, if somebody wants to generate a range of numbers between 0 and 10, they'll be able to do that.
Awesome. Okay, well, with that, that is going to wrap up this video.